Hi all, this is Mr. Yeager for Physical Science, looking at chemical reactions, introducing chemical reactions today. We're going to look at basically what are chemical reactions. We've talked about it some already in another video with chemical changes. Obviously those are chemical reactions. But we're going to get into writing and balancing chemical reactions as well. So again, we're going to look at what makes it a chemical reaction and then how do we write these out. Okay, so here we go. So in my classroom, the first thing I do is I show them a neat chemical reaction called the barking dog reaction. You can look that up on YouTube and you can check that out yourself. It's a neat one that has light, that has the sound to it because of the pressure inside a tube, and shows gas formation. It has all sorts of things happening to illustrate a really neat chemical reaction. So this reaction is one of many chemical reactions, and a chemical reaction is the process where the atoms essentially rearrange and they form new substances. All right? So we have gone over atoms now, we've gone over compounds now. What's going to happen is those compounds, with the elements in those compounds, they might rearrange and combine with a different element, and as we know, that means it's a new compound. This is the exact same thing as we already talked about before back in the matter unit. That's also called a chemical change, which I think I have a crazy animation here. Okay, chemical change, come on. There we go. Oh, there we go. Chemical reactions, chemical change. Okay. So then we kind of look at, here's just different examples of chemical reactions occurring. You put gasoline in your car, clearly there's something different that comes out. That would be the exhaust and everything, the carbon monoxide, carbon dioxide, and water and other things that are released by the car. But that gives the car energy as well. Down at the bottom, wildfires. Okay, anything with fire, as we said, involves a chemical reaction. Afterwards, that's turning the trees into ash, which is something completely different than what was the organic material that was the tree itself. If you eat some hot dogs, at the end of it, you know, I'm not going to show that picture, but clearly it comes out as something different, and you use those chemicals inside you, you rearrange them to do different things for your body to give yourself some energy. Okay? So, how do we know reactions take place? All right? Again, we went over this some with chemical changes. The main things would be that there is a clear temperature change occurring without you physically trying to change the temperature. So this is where you mix the two objects and they get hotter because you mix them, not because there's a flame underneath of them, not because it's on an oven or a hot plate or anything else like that. It's changing its energy on its own. It's changing its temperature on its own. There are two types of temperature change reactions. All right, we got what's called an endothermic reaction. All right, in an endothermic reaction, you absorb energy. Okay, and what happens is the object itself will feel colder. Now, again, that might sound confusing because you're like, oh, I absorb energy. Shouldn't that mean I get warmer? The idea is that the chemicals are pulling the energy inside of their bonds, which therefore then means you cannot feel that heat anymore, and the object feels colder. Okay, it actually is gaining energy, but it feels colder because it's pulling in that heat. Exothermic is the opposite. Exo, exit. That means the energy is being released during the reaction, where actually the elements, the chemicals involved are losing energy, and therefore it's losing energy to the environment and it feels warmer. Other signs of evidence: color change, odor, gas bubbles, and appearance of a solid, which we call precipitation. All right. If any of these things occur, again, without you physically trying to change the temperature of the object by having it on a hot plate or anything, these are signs that a chemical reaction occur. All right. So here's just some neat pictures of some. I know maybe it's a little blurry. You got these two clear liquids being mixed together. All right, lead nitrate and potassium iodide. They start mixing. You can already see that the color is changing a little yellow in that picture when the two things are mixing together. Right there you can see that it's really turned yellow, and it's actually forming a powder. That's actually a precipitate being formed. And so you have color change, precipitate, solid forming, all those from liquids, all those being signs of a chemical change. If I do phosphorus and oxygen, this one's a very violent reaction. All right, obviously you can't really see it very well, but the idea is this first flask has oxygen in it, pure oxygen gas. And then you can't really see it, but there's phosphorus, little pieces of small solid phosphorus in the other jar. Basically, you turn off the light, You start mixing it in. Almost immediately when you mix that phosphorus on in, it will ignite in the oxygen. The oxygen goes basically, attacks it. There's a lot of electrons basically being shared and moving very quickly, and therefore it creates a very large flame. And again, that's a sign that you have an exothermic reaction and gas formation, signs of a chemical change. So that's again telling us, that's a kind of a review that we've talked about before, signs of a chemical change. But how do we then show these chemical reactions? All right. So we have what I call the players. We have reactants. These are going to be our starting substances. We have products. These are the things that are formed after the reaction. We also will have something in the written chemical reaction called yield arrows. This is just the arrow showing how the reaction is going from reactants to products. All right. It is possible that you might also see the physical states of the reactants and products listed. All right. Where what happens is we might write H2O and then in parentheses right next to it L. That's meaning that this water, this H2O chemical, is a liquid at this time. That's not done as much in physical science, but in chemistry we often use that to really illustrate where something is changing, especially in honors chem where you might have to show that it becomes a precipitate. All right? We'd want to show what state of matter that object is changing into to show the chemical reaction taking place. So you can see the letters. We just usually take the first first two letters. Solid S, L liquid, G gas, and AQ means the chemical is dissolved in solution, dissolved in water. When we put these reactions together, we always write this reactants going to products. Reactants on the left, okay, arrow, products on the right. All right, we will never show it going the opposite, well, it can go the opposite way, but we're not going to show that. But we never write products, arrow, reactants, or product. You know, we're not going to write products, arrow going to the left, reactants. That would not be right. What we will eventually write is something called a chemical equation. All right. So we have, just to review, we have chemical symbols. That's where it's just the element, like Al. We have chemical formulas. That would mean that we have a compound, like CaO. Okay. Now we have a chemical equation. A chemical equation is showing you what formulas are involved, what chemical formulas are involved, and what are they becoming. So basically, to write one of these out, we go step by step. All right. Well, sorry. Wait a minute. What this is trying to show you, we're not getting to steps yet, is two things. This will help you identify the elements, the reactants and products, and will also, it'll show how many of each of these compounds are reacting, because we might have 2 water molecules reacting with a calcium oxide or something like that. All right. The reason we're doing that is because we have to follow the law of conservation of mass. All right. That we have to follow this law of conservation of mass. So what is the law of conservation of mass? It's when, it states that the mass must be conserved before and after the reaction. All right. The total amount of reactants must equal the total amount of products. That is obviously the ideal situation. It is happening, but what happens is sometimes some of the stuff changes into energy or we don't measure it correctly. But in a true reaction, we should have equal amounts of reactants and equal amounts of products. This is why we balance chemical reactions. So if you have a question of why are we balancing the reaction, why can't I just write what's on the reactant side and what's on the product? Why do I have to write the number that's amounts of each one? We have to show that every atom is accounted for. All right, that the total mass before equals the total mass afterwards. So here we go. We have a chemical equation. So the easiest way to learn, just like chemical formulas, is just doing one. So I have a chemical equation here. You can see I have iron, which is in a solid state. I have chlorine, which is in a gaseous state. And then I have iron 3 chloride, all right, which is in a solid state. So solid iron is going to react with gaseous chlorine to form solid iron 3 chloride. All right. Now, you don't have to worry about where that equation came from, but that's the one being given to you. So the correct answer is going to be that we need 2 irons, 3 chlorines, and 2 iron 3 chlorides. Where the heck did I get that from? Okay? So first off, what are these numbers in the first place? Why did I even write them? Okay? These numbers in front of the atom, in front of the compound, written very large, not like a subscript. This is a subscript saying that you have 2 chlorines. Okay? The number in front written very large is called a coefficient. All right? It will only ever be whole numbers. So we cannot, just like subscripts, we cannot have 1.5. Okay? We can't have 1/2, 1/4. It has to be 1, 2, 3, 4, 5, 6, 7. Okay? Also, as always, we never write the coefficient 1. If I'm writing iron up here, if I write iron, clearly I have at least 1. So all I need to do is tell you if I need another one, if I need 2, 3, 4, 5, and 6. And like chemical formulas, we need to have the lowest whole number ratio of these coefficients. What that means is, if I can divide a number into 2, 3, and 2, if I can divide the same number into all of them, and if I divide it and I still have a whole number, I need to do that. I need to reduce it. All right? The thing is, if I divide all 3 of these by 2, this would become 1, this would become 1.5, which is immediately wrong, and this would become 1. So that doesn't work. We would not reduce this particular problem. We are good. All right? But if we can reduce it, if they're all even numbers, if this was 2, 4, 2, we would reduce that down to 1, 2, 1. All right? So we do have to check the ratio at the end. That's, again, another little mistake where the reason is, why are we doubling it when we don't have to? Why are you adding more chemicals when clearly you're adding too much? All right, so here we go. How do we actually balance the reaction? How did I know it was going to be 2, 3, 2? We look at the chemical equation. Okay? The first thing to do is really count the number of atoms that you have on the reactant side and the product side. If it happens to be exactly equal, you're done. There are some equations where the equation as written is correct, is balanced. But in this one, we can see we have 1 chlorine and we have 1 iron and 2 chlorines in the reactant side. 1, 2. And then on the product side, we have 1 iron and 3 chlorines. So this is not balanced. While the irons are all good, the chlorines are not balanced. All of a sudden, I have 1 more chlorine on the product side that's not on the reactant side. So that doesn't make sense. So here's the big step. I mean, I could put it down as one giant step here. We change the coefficients in front of the atoms, or in front of the compounds, which, again, right now it's all 1, 1, 1. All right? We change the coefficients to make the number of atoms of each element equal on both sides. We never change the subscripts. We're not, I mean, I actually have seen students come up and be like, no, done. And that's not correct. I'm going, what are you doing? All right? You cannot mess with the subscripts after they are written. All right? So we never touch the subscripts. We can look at, basically, we will be looking at lowest common multiples of atoms. So you're going to get used to the idea of what's the least common multiple between 2 and 3. This is something that you probably did back in middle school. Okay? So between 2 and 3, that would be 6. You're going to see the same trends. We're going to be looking at trends of what's the lowest common multiple between 2 and 3, what's the lowest common multiple between 3 and 4, what's the lowest common multiple between 2 and 5, okay? It's going to be simple numbers. It's not going to get ridiculous. I mean, we could make it ridiculous and get to very high numbers, but most of the times we're going to be just doing 2 times 3 is 6, and so forth. So the way I kind of go through it, and it's a little tough to see it through the video, is basically, instead of really there's all different methods for it. What I essentially go with and find that most students do the best with is I just take my time and go, how many irons do I have? I have 1. I go to the other side of the arrow. How many irons do I have? I have 1. So right now, I don't need to do anything. Irons are all good. No new coefficients. How many chlorines do I have? I have 2. How many chlorines do I have? I have 3. So I do ask myself this question. What's the least common multiple between 2 and 3? And that is 6. I'm not saying write 6. That's not right. What I'm saying is, what times 2 is 6? The answer would be 3. What times 3 is 6? That would be 2. And don't think this is a whole just crisscrossing thing. I mean, it's very close to that in some cases, but it's not always. All right. But it's the idea that now I have 3 chlorines. I have chlorine 2, chlorine 2, chlorine 2. That means I have 6 chlorines. Over on the other side, I have FeCl3, FeCl3. I have 2 of these compounds. 3 plus 3 is 6. They're the same amount. But I'm not done. All right? Because now that I added this 2 in front of this compound, this 2 goes to both atoms. So I have 6 chlorines, but also if I look up here, I have 2 irons now. So now I have 2 irons on the right-hand side, so how many do I need on the left? 2. And there is my reaction. 2, 3, 2. Okay? So it's a lot of going back and forth. This is going to be very common where you get one balanced and an unbalanced is another, and you just keep on going, all right, until everything is balanced. Confirm that's the lowest whole number ratio. I can't divide everything by the same number, okay? So that's not going to work and still have whole numbers. So I'm good. And the last thing, check it one more time. Go through it and go 2 Fe's, 2 Fe's. 6, 3 times 2, 6 chlorines, 2 times 3, 6 chlorines. So the coefficient and the subscript get multiplied together, not added, get multiplied together to give me the total number of atoms that I have. Check your work. So if we practice some, what I have is, I have 2 hydrogens. I have 2 hydrogens. So that's all done. I don't want to touch anything yet. At least it's good for now. I have 2 oxygens. I have 1 oxygen. So I need more oxygens on this side. Well, how many do I need? I need 2. So this is, like, again, be careful. The idea is there's a subscript 1 right here. What times 1 is 2? 2. The thing is, now that my oxygens are good, how many hydrogens do I now have? I have 2 times 2 is 4, so I need to multiply this side by 2. Let's check my work. 1, can I reduce it? No. If there's a coefficient of 1 in your answer, when it's all balanced, it's definitely lowest ratio. But let's double check anyway. 4, 4, 2, 2. 2 times 1 is 2. All right, how about this next one? This is a little mistake here. This should be Al2, lower down below. All right, let's look at this one. I have 1 Al, I have 2 Al, so I'm going to put a 2 in front of this. So aluminum's balanced. I have 2 oxygens, 3 oxygens. Lowest common multiple, 6. What times 2 is 6? 3. What times 3 is 6? 2. But hey, now I messed the aluminum up. Now I have 4 aluminum, so I come back and erase this and write 4. And now I'm all balanced. And I can't divide everything by 2. Like, it's basically, can you divide by the smallest number? Nope, I can divide 4 by 2, but I can't divide 3 by 2 without getting a decimal. So 4 aluminum, 6 oxygen, 6 oxygen. All right. Let's see what I got here. All right, this one's a little bit tougher. This one can be a little bit tougher. All right. What about this reaction? This is actually the barking dog reaction at the beginning, which is why I give it. So this one's a little bit tougher, okay? I will give you a little hint, a big hint that I always use to balance chemical reactions that can really help you out, all right, is always balance sorry, let me say it again. If there are any compounds or elements that are, I'm going to say this one more time. I'm messing up here. If there are any elements alone, balance that last. Balance them last. Okay? So what that means is I look at all of these chemicals. It's like, oh my gosh, I got to balance carbon, I got to balance sulfur, I got to balance oxygen. We want to balance oxygen last, and that's because when I put a number in front of CS2, I am affecting C and S. When I'm putting a number in front of CO2 and SO2, I'm affecting 2 atoms, not just 1. If I put a number in front of oxygen, I'm only changing the number of oxygens. So I'm going to do that one last. So if I look at this, I have 1 carbon, all good. And I do have to look at all the stuff over here. I have to look at all of it over here. I only have one source of carbon, one. I have 2 sulfurs, I have 1 sulfur, so I need to add a 2. Okay? It doesn't go back and affect carbon, so I'm all good. So all I have left is oxygen. I have 2 oxygens on the left side. I have 2 oxygens from this compound, and I have 4 oxygens from this compound. So 2 plus 4 is 6. So what times 2 is 6? 3. Solved. Okay? So there's my, and you can see I can't reduce it. I have 1s. It's all good to go. And that's it. All right? So balancing chemical reactions, follow those steps well, take your time. I will say, if you make a mistake where you're like completely stuck, the best advice I can give you, where if you're like sitting here and putting like a 2 over here, sorry, if you're putting like a 2 on this side, okay, and then you're putting like a 3 on this side, I didn't let it load, and you're getting all confused, the best advice I can give you is just erase everything and start over again, okay? It's going to get too messy to try to figure it out where your mistake was. It's so easy. It's much easier just to erase and start over again. All right, that's it. Have a good day.